Hello and welcome back. Today's episode on electronics, we're going to look at how signals turn to logic. So far, we looked at a few episodes where we discussed how signals are based on waveforms, how we talked about diodes, transistors, amplifiers, all sorts of variations in electronic components. Today, let's look at how does it turn into logic? How do we build computers? How does it become digital? So, have you ever thought about the moment when an electronic component stops being just wires and components and starts making actual decisions? Is it even possible, right? Not just lighting a bulb or powering a motor, but deciding what to do, comparing values, storing data, calculating, all sorts of things. So, this is the moment electronics begins to think. And today we are stepping right into that transformation from analog into digital. It is actually two different worlds. We live in a continuous world. If you look at sound, it kind of blends smoothly. I'm talking or I have music. All the waveforms, they blend very smoothly. It is not discrete. I'm not talking in staccato, like I don't speak in short bursts, but it is continuous. Let's look at light. Something very similar. Light is also continuous. If you look at the Vibgyor spectrum, you start from violet, you keep going all the way to red. But is there any specific place in the spectrum where red or violet turns into blue or indigo, or is there a specific place where orange turns into red? No, it continuously gradually changes. At some point it becomes red, or it feels like now it is red, right? So there are infinite values between any 2 points. That is the analog world. Temperature, thermometer, you put it in your mouth to measure your temperature, right? So that rises gradually. There is no specific number saying, okay, now this guy has fever. No, that doesn't work like that. But we have come up with a threshold saying this is a number beyond which this person qualifies to have a fever. So that is the analog world. It is messy. It is very rich and full of detail. There are so many infinite values between 2 points. But electronics, especially digital electronics, they don't operate in that analog world. They prefer clarity. When you are counting, you prefer clarity, right? There are sharp edges, clean decisions. So digital electronics, they live in a world where something is either low or high, 0 or 1, off or on. So that raises a question. If our world is smooth, continuous, and the digital world is binary, how do they understand anything at all? So the answer begins with something called as thresholds. So a threshold, this is where analog becomes digital. Threshold is an imaginary line or a number we call up. So let's talk about it. Imagine slowly turning up a dimmer switch. You have a light in your home with a dimmer switch. If you keep turning it, at some point the light becomes bright. At what point does the light suddenly count as bright? Is there a specific number in your mind? Not really. You feel it is bright at some point. So digital circuits do the same with voltage. They define very clear boundaries. So they say that, okay, I'm going to get an analog voltage starting from 0 to 10 volts. So below a certain voltage, let's say below 0, I would call it as 0. Above a certain voltage, I will call it as high. So let's look at 5 volts as this threshold. I have a wire which can carry from 0 to 440 volts, for example, right? So anything above 5, I just count it as 1. Yes, there is voltage, it's on. But anything below 5, I just call it as 0. It doesn't matter. It may be 4 volts, 3 volts, 2, 1, it doesn't matter, it's 0. Anything above 5 volts, I call as 0. Now it is suddenly easy to measure, right? I don't have to worry about whether it is 4.8 or 4.9. Should I call it as high or should I call it as low? All the decision making becomes much simpler if you define a threshold and say anything above a threshold is a certain value, anything below a threshold is a certain value. Anything else in between? Noise, just ignore it. So this single idea, turning messy analog values into clean digital decisions, this is the bridge between real world and the digital world. So this is kind of the moment where a wire stops carrying voltage and it starts carrying information, right? You have a wire, it is carrying voltage from, let us say, 0 to 440 volts, but you put an imaginary threshold and you said anything above 5 volts is a 1 for me, anything below 5 volts is 0 for me. So that is information. Now suddenly the wire is carrying information like 0 or 1 instead of voltage, right? So that is the moment where the wire stops carrying a voltage and starts carrying information. Now let's look at how does it translate into higher level logic gates. These are the first electronic thoughts that can occur. Once a signal becomes a clean 0 and 1, circuits can start thinking. Do you know how? So in earlier episodes, we built up from P-type semiconductors, N-type semiconductors. We built it into diodes, transistors. Now we put them all together to create something far more powerful called logic gates. If you remember, diodes allow current to flow in a one way, in one direction. Transistors allow us to modify the base current and increase the output current. So you can amplify, or you can also use it to turn it on and off. In a transistor, on the base, if you apply a voltage, you can basically decide whether current flows from the emitter into the collector or not. So you can turn it on and off. So you suddenly have ones and zeros available through the transistor, right? Now let's put them all together to create something far more powerful. Logic gates. So logic gates are tiny electronic circuits that take one or more digital inputs and they produce a single digital output based on a set of rules. So what are these rules? I will talk only about the three major rules. There is going to be a lot more, but for us to understand the concept, let us look at three: AND gate, OR gate, and NOT gate. So AND gate. So understand how a AND gate works. Let's look at it. If you have two wires, both of them carrying voltages from 0 to 440, we decided that we have a threshold of 5 volts. Anything above 5 volts, we call it as 1. Anything below 5 volts, we call it as 0. So with that assumption, we have a wire that is carrying voltage, and if both outputs are one is carrying 5 volts, the other is carrying, let's say, 10 volts. If you add it together, you have 15 volts. But remember, we said that there is a threshold of 5 volts, and anything above 5 volts, we just call it as 1. It's just on for us. It doesn't matter whether it is 15 volts or 440 volts or 5.2 volts. It's all the same for us. So if you add up two wires carrying this value of 1, what we get as output is also 1. That is an AND gate. So similarly, if one of the wires is carrying 1 and the other one is carrying a 0, remember this is an AND gate. This is like multiplication for us. If you multiply these two voltages, 1 and 0, we get a 0. So similarly, if one is carrying 0 and 1 or 1 or 0, you will always get 0. But if both are carrying 1, you will get 1. So that is an AND gate. Both are 0, anyway is 0. Similarly, let's look at an OR gate. So this time, one of them is carrying 1, the other wire is carrying 0. But this is an addition. So 1 plus any other voltage, you are still at 1, right? Similarly, a NOT gate, which will flip the meaning. You have 1 coming out of a wire, you pass it through a NOT gate, it will flip and make it 0. Or if you have no voltage coming out of one of the wires, you flip it, its meaning becomes 1. So that's a NOT gate. So these are the basic three gates that are important for us. These tiny rules, they form the alphabet of our digital logic. Our entire digital logic and truth tables and whatever that follows is based on this binary logic. So just like letters forming words, logic gates combine to form more complex decisions. So let's look at that. How does a simple gate build complex intelligence for us? So one gate makes a simple decision. You have an AND gate, you give it two voltages, it makes a decision whether the output is 1 or 0. You put together a few of these gates and you can start comparing values. You put together a handful of these gates and you can start adding numbers. So let's take a classic example of binary addition. What do you mean adding numbers? We have only zeros and ones, right? If you can take a digit like 8, and if you can represent that in zeros and ones, so if you take another digit like 5, if you can represent that in zeros and ones, pass it through these gates as alternating zeros and ones, you can actually start doing binary addition. And if you can convert that back into your decimal number, you will actually get addition, or the number that was added together. So the rules for adding two bits are very simple. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0 with a carry of 1 for XOR. But for addition, it is 1 plus 1 is also 1. So all of these rules can be encoded using the same logic we talked about, using the same threshold measurements we talked about. They all become half adder and full adder circuits. I mean, you can refer to the books for complete details on how a half adder works or how a full adder works, because I intend to keep these episodes simple enough to introduce you to the concepts. You can dig deep into how the details of these circuits work. And if somebody wants a more detailed explanation on a particular concept, please do put a comment out there and I'll respond to that. Now with a chain of 8 of these half adders, you can actually start doing 8-bit number additions. You chain 32 of them, you get 32 bit adders. So the same idea, the more you scale it, the more complex addition, subtraction, multiplication it can do. So scale the same idea upwards and you get arithmetic units. You scale it further, you can get a comparator, you will get to registers, ALUs, CPUs, and entire computers. So it all begins with simple gates following those simple rules. That's the beauty of analog to digital. Now let's also look at logic in the real world. So we're talking of CMOS here. So logic gates on paper are one thing, but in real life it's much more complicated. So over the years, engineers have developed several similar logic families to physically build logic using semiconductor technology. Remember, you just need to have an awareness that there are many types of semiconductor technologies, TTL, ECL, and CMOS. But CMOS is the one that is used in most of our electronics. So CMOS basically is a complementary pair of P-type and N-type MOSFETs. Again, please go to the reference books and look up what is a MOSFET, because it just takes a lot more information to put into this episode, but I won't be able to keep it short. So refer to that, but if you want me to have a separate episode dedicated for a deep dive on these topics, I can definitely do that. So that's CMOS, basically complementary pairs of P-type and N-type MOSFETs. And this is what you will see in most of your phones and laptops for digital decision making. So every gate you have interacted with is ultimately made of these tiny P-type and N-type transistors, switching on and off a billion times per second. Yes, that's correct. Billions of times per second it switches on and off, giving you that stream of 1, 0, 0, 1, 1, 0, all of those things. So scaling up from a single gate to a billion of them, we get a lot of progress. So the astonishing part is this: a single transistor can switch, a few transistors can make a gate, several gates can make a adder, half adder, full adder, thousands of them, they give you an arithmetic unit, millions of them give you a processor core, billions of them form a modern CPU. So today we just blindly use the laptop or computer with a modern CPU in it. What we fail to remember is that most of these processors contain over 100 billion transistors. 100 billion, that's correct. Each one is a microscopic switch built from the same P-type and N-type materials we discussed in earlier episodes. No magic, it's all there in the previous episodes. It's just that the scale has been blown up to 100 billion transistors and it can do a lot. It works like magic. So all of them are also built on the same idea of zeros and ones. You have a low and a high, you have an on and an off, you have a threshold, and that allows us to build digital logic using these electronics. That's the staggering simplicity behind very powerful computations that we do today. So the next time you unlock your phone or stream a video or play a game, remember this: behind the smooth experience lies an entire universe of microscopic decisions, tiny gates firing endlessly, converting signals, making comparisons, flipping bits, adding numbers. And what are we doing? Making a call, playing a game, streaming video. Every part of the digital world, from the simplest calculator to the most advanced AI system, is built on that idea that electricity either flows or it doesn't. That's it. And from that binary foundation, we have built everything, this whole beautiful digital world around us. I hope you appreciate the beauty of that. So I'll stop here. This has been a very high level awareness of digital logic and converting signals from analog to digital. So do come back for more. I'll put together the next episode for you. Thank you for watching. Do subscribe, leave some comments so that we can start interacting. Thank you.